In the name of God, my name is Mehdi Kornavasi, and in this movie, I will talk about the introduction to database management system, functional dependency, and normalization. Let's start. The purpose of the database design is to arrange the various data items into an organized structure so that it generates set of relationship set and store the information without any repetition or duplication. A bad database design may result into redundant and spurious data and information. Normalization is a process for deciding which attributes should be grouped together in a relation. Normalization is a process for deciding which attributes should be grouped together in a relation. This is a definition of normalization. It is a tool to validate and improve a logical design so that it satisfies certain constraints that avoid redundancy of data. So all we will do in normalization is to avoid redundancy of data. Each data must be stored only in one place in a database without any duplication. Normalization is defined as the process of decomposing relations with anomalies to produce smaller, well-organized relations. Thus, in normalization process, a relation with redundancy can be refined by decomposing it or replacing it with smaller relations that contains the same information but without redundancy. What is the anomalies or inconsistencies in relational database? Anomalies refer to the undesirable results because of modification of data. Anomalies are as follows. Insertion anomaly. Suppose you want to add new information in any relation but cannot enter the data because of some constraints. In relation employee, you cannot add new department finance unless there is an employee in finance department. Here is an example of a table about the entity employee, and you cannot add a department named finance unless you assign an employee with a salary to them, because we cannot add a record to this without value. The next anomaly is deletion. The deletion anomaly occurs when you try to delete any existing information from any relation, and this causes deletion of any other undesirable information. For example, in relation employee, if you try to delete tuple or a record containing Deepak, this leads to the deletion of department sales completely. There is only one employee in sales department. Look at here. If you delete this item, this employee, you will lose the sale because there is no other sales department in other records. The next is updation anomaly. The updation anomaly occurs when you try to update any existing information in any relation, and this causes inconsistency of data. For example, in relation employee, if you change the department number of department accountants, look at here, there are 4 accountant department in this table. If you want to change or update the name of this department, you have to update all other records. Note, we can update only one record at a time. This will cause inconsistency if you update department number of single employee only. Otherwise, you have to search all employees working in accounts department and update them individually. Normalization first normal form, or 1NF. First normal form is a relation. First normal form if domain of each attribute contains only atomic value. It means atomicity must be present in relation. It is not in first normal form because attribute name in one is not atomic. So divide it into 2 attributes or 3, first name and last name, as shown in the below. Let's see, here is a employee table, and we have some fields: employee ID, first name, second name, salary, department number, and department name. So if we had only one name, including first and second name together, the relation is not in normal form because we can separate a field to another or more than one field. So the anomalies in first normal form deals only with atomicity. So this relation or this table is 1NF or normal form. The higher level is normalization in second normal form or 2NF. Second normal form is a relation is in second normal form if it is in 1NF first, and all non-primary key attributes must be fully functionally dependent upon primary key attributes. Consider the relation student as shown in below. The primary key is roll number and game. It means each student can participate in more than one game. Relation student is in 1NF, but still contains anomalies. As you see, all fields in is atomic, but there is some anomalies. Why? The first is deletion anomaly. Suppose you want to delete a student Jack. Here you lose information about game hockey because he is the only player participated in hockey. As you see in the picture, here only we have one name, Jack, and if we want to delete the Jack, we will lose the game hockey because Jack is part of a line or a record, and with deletion of this record we will lose the definition of roll number 5 with game hockey. The next anomaly is insertion anomaly. Suppose you want to add a new game, basketball, having no student participated in it. You cannot add this information unless there is a player for it. So if you want to add a game here, basketball, you have to find a player, at least one player, and fee and grade to add a new record. The next anomaly is updating anomaly. Suppose you want to change fee of cricket. Here you have to search all the students participated in cricket and update the fee individually. Otherwise, it produces inconsistency. Here, there are 3 records with cricket. One game, but it's repeated in 3 records. And if you want to change the fee, the first is 200, the next is 200, the third also is 200. If you want to change the fee, for example, from 200 to 210, you have to update all 3 parts. The solution of this problem is to separate partial dependency and fully functional dependency. So divide a student relation into 3 relations. A student with roll number and game and name. The second is game with the field game and fee, and performance with 3 fields: roll number, game, and grade. Now, deletion, insertion, and updation operations can be performed without causing inconsistency. Look at this picture. If we divide one table into three separate tables. One table just with defining the students, roll number and name. Another table just for the definition of the game fee, and another as a relation table. So roll number 1 game cricket with grade A. Roll number 2 game badminton with grade B, and so on. Here, if you change, for example, name of Jack with roll number 5, so you don't need to change or delete something. But if you delete the roll number 5 from table student, here roll number 5 has no any name, student name, and we will have with another issue. So we need to increase the level of normalization. And it is a third normal form, or 3NF. A relation is in third normal form if it is in 2NF and non-primary key attributes must be non-transitively dependent upon primary key attributes. In other words, a relation is in 3NF if it is in 2NF and having no transitive dependency. Transitive such that if it applies between successive members of a sequence, it must also apply between any two members taken in order. For instance, if A is larger than B and B is larger than C, then A is larger than C. We say this is a transitive relation. The primary key is roll number in this example. The condition is different hostel is allotted for different semester. A student relation is in 2NF but still contain anomalies. Here is another example, and there are some students, roll number and name, and some hostel. In each semester, we need to assign a roll number and hostel. Here is a primary key. Roll number is related with name. Also roll number related with semester, and roll number related with hostel in each line or record. On the other side, semester is another primary key and related with hostel. So let's see the anomalies. The first is a deletion anomaly. If you want to delete a student graph, you want to delete this student here. What happened? You lose information about hostel H2 because He is the only student staying in hostel H2. The next anomaly is in insertion anomaly. If you want to add a new hostel H8 and this is not allotted to any student, you cannot add this information. If you want to add H8, for example here, and you have not any student related to that, you cannot add to this table. And the next anomaly is updating anomaly. If you want to change hostel of all students of first semester, you have to search all the students of first semester and update them individually. Otherwise, it causes inconsistency. Here, to record with semester 1 with hostel H1 and 1 again with hostel H1. If you want to change, you have to change both records. The solution of this problem is to divide relation student into two relations: student with 3 fields, roll number, name, and semester, and hostel with 2 fields, semester and hostel. Here is an example. We separate this table with 2 tables, the one for a student and the second for the hostel. So we can resolve the anomalies in this level. The higher level of normalization named Boyce cut normal form or BCNF. BCNF is a strict format of 3NF. A relation is in BCNF if and only if all determinants are candidate keys. All determinants are candidate keys. BCNF deal with multiple candidate keys. Relations in 3NF also contains anomalies. Consider the relation student as assumption, 3 assumptions. The first, a student can have more than one subject. The second, a teacher can teach only one subject. And the third, a subject can be taught by more than one teacher. Let's see what happened. Here is a teacher. Many students, roll number and subject assigned to teacher. And here is a subject. Again, roll number and teacher assigned to the subject. And as you see, we have an overloaded candidate key of roll number here. There are 2 candidate keys, roll number, subject, and roll number and teacher. Relation student is in 3NF, but still contain anomalies. The first is a deletion anomaly. If you delete a student whose roll number is 7, you will also lose information that teacher T4 is teaching the subject, for example, Visual Basic. Let's see in the table. Roll number 7, if you decide to delete this, you will lose the subject VB and teacher T4, because both of these are related to one roll number 7. And the next anomaly is insertion anomaly in this form. If you want to add a new subject, for example, VC++, you cannot do that until a student chooses subject VC++ and a teacher teach subject VC++. If you want to add a new course here, you need to assign at least one student and one teacher. Otherwise, you cannot add a new subject here. And the next anomaly is updating anomaly. Suppose you want to change teacher for subject C. You have to search all the students having subject C and update each record individually. Otherwise, it causes inconsistency again. For example, here, the subject C repeated 2 times. Roll number 1, roll number 3. Again, this subject is taught by teacher T1 and T1. And if you want to update subject C, you need to update both records. In relation student, candidate key is overloaded, as I showed in the picture. You can find teacher by roll number and subject. You can also find subject by roll number and teacher. Here, roll number is overloaded. You can also find subject by teacher. So, what's the solution? The solution of this problem is to divide relation student in 2 relation student teach and teach subject. As you see, we divided one table in 2 different tables. This table is a relation table between roll number and teacher, and here is another relation between teacher and subject. In this solution, all determinants are candidate keys. We say this is in a BCNF normal form. Okay, let's see the higher level of normalization is fourth normal form, or 4NF. A relation is in 4NF if it is in BCNF. And for all multi-valued functional dependencies, or MVD, of the form X to Y, either XY is a trivial MVD or multi-value dependency, or X is a superkey of relation. Relations in BCNF also contains anomalies. Consider the relation project works as shown. Here is a project, programmer P1, P2, P3, P1, P4. We have 4 programmers and we have 3 projects and we have 2 module. So let's see assumption. A programmer can work on any number of projects. A programmer can work on any number of projects. For example, here P1 is worked on project 1, again P1 is worked on project 3. And the next assumption is a project can have more than one module. A project, for example, project 1 have module M1 and module M2, or project 3 have also module M1 and module M2. These are assumptions. Relation project work is in BCNF but still contains anomalies. Let's see deletion anomaly. If you delete project 2, you will lose information about programmer P3. If you delete this project, you will lose P3 because P3 is only one programmer assigned to this project. The next is insertion anomaly. If you want to add a new project 4, you cannot add this project until it is assigned to any programmer. And the next, updation anomaly. If you want to change name of project 1, then you have search all the programmers having project 1 and update them individually, otherwise it causes inconsistency. Dependencies in relation, project work are programmer project and project module. Programmer project and project module. The solution of this problem is to divide relation project work into 2 relation proj or programmer project and proj module or project module. As you see here, we separate in 2 different tables. Programmer here is a super key and project here is a super key. They are not primary key because repeated more than one. Primary key we have only one time in each record, but there are super key instead of primary key in this relation. The last level of normalization is project join normal form or 5NF and join dependency. Let's see join dependency. Let R be a given relation up to 4NF and it decomposes project or divided into a set of R1, R2, R3 to Rn. The relation R satisfy the joint dependency star of the relation if and only if joining of R1 to Rn equal to R. It means if we separate dependency and then rejoin again, the result be as a same relation. Consider the relation x, y, z. Here is a relation x, y, z with attributes x number, for example, customer ID, y number, for example, account ID, and z number, for example, branch ID. In this relation, we have x1 and x2, y1, y2, and z1 and z2. Here is the original table. And we want to first decompose x, y, z into three relations x, y, y, z, and z, x. We decompose, and let's see here x1 and y1, x1 and y2, and x2 and y1. Just three records come here because x1, y1, there are two records. Okay. And for yz, as you see, y1, z2, y2, z1, and y1, z1. We don't need to add the duplicate records. Again, in zx, z2, zx, z2, and x1, z1 and x1, z1 and x2. z1 and x1 is duplicate record, so we decompose the original into three separate relations, and then we will try to join. The first, we will join these two tables together, xy and yz. So xy come from this table and z come from this, x1, y1, z2. Again, x1, y1, z1, two records. And x2, and again, x1, y2, x1, y2, z1. Here, three records come here. And the next, x2, y1. Because we have two y1 here, so two records come here with x2. x2 come from y1 and z2, and x2 come from y1 and z1. Here, we join this relation, and as you see, the original table x, y, z is different than the join relation. We have one more record after joining. So this is not an original table. And if we join our z number and x number, let's see x1, z2, with z2 we have y1. So x1, y1, z2. x1, z1, we have y2, x1, z1, y2, and x2, z1, y1, x2, z1, y1, and we have x1, y1, z1 also. Why? Because in this line x1 and z1 have a relation with y1, so x1, z1, y1. After joining the original table x, y, z, as you see, these two tables are the same. So let's repeat the procedure. First, decomposing x, y, z into three relations x, y, z, and zx. When joined, these three relations give original form of x, y, z. So relation x, y, z satisfy the joint dependency. Project joined normal form or 5NF. Let R is a relation and D is a set of all dependencies. It means multi-valued dependencies, functional dependencies, and joint dependencies, and etc. The relation R in 5NF if for every joint dependency in trivial. 5NF is the ultimate normal form. A relation in 5NF is guaranteed to be free of anomalies. Consider the example and we watch the example. So in reality, we must design the relationship between the attributes, entities, and then we need a simulation and a relation, make a relation and try to add some example records. This is my own experience, and trying to test all anomalies, delete, insert, and update, and testing for the redundancy of the data. And this is not easy job and needs a lot of experience of designing and implementing the databases. Okay, we reach to the end of this chapter, and thank you for watching this movie.